So let's start with this exercise. How do we solve this? One advice that I can give you is try to find some expressions that can be related. For example, you can find expressions related to Theorem 4 in a way that you have one term, for example, you have A, and on the other side you have two terms. So you can find, for example, I can tell you this one here with this one here might be that case, because remember, A can be a series of expressions. So if this part here repeats again in this part, well, that means that you have the same, you have A and A. However, this is not the case. So first we take a look at this expression here, and we also take a look at this expression. So the question is, what can we relate in this expression with some of the theorems? And if we take a look at Theorem 7, you can see that this expression is similar. You have something that repeats in both sides. In this case, the thing that repeats is W. Something that is inverted, which is the Y. You have Y inverted here, and you have Y inverted on the other side. And something that is not on one of the sides. So when you have this, if you see Theorem 7, what gets out of the equation is the inversion. So in this case, you can say by using Theorem 7, this expression is going to be reduced to W Y inverted, and then you're going to remove the inversion. In this case, the inverted variable is the Y. So you reduce that expression to that. And of course, you write the remaining part. Now we can use the same theorem with these two expressions. This one here and this one here. You can say I'm going to use Theorem 7, and of course I'm not saying here, but you should also put that you're using part A of the theorem, and this expression is going to be reduced to, again, in Theorem 7 you have to look to what it's inverted. So the Wx appears on both sides, the zeta is inverted in one side, and so the inversion is going to be taken away. So this becomes Wx y, the zeta is inverted, so I'm going to take that away, Wx zeta inverted. And of course I write the remaining part, which is the same. So now we're going to use again Theorem 7. We're going to use Theorem 7 with this term here and with this term here. And again, the inversion is going to be removed. So Wy inverted remains, and Wxy, it's only Wx. I write the remaining part. And I'm going to use again Theorem 7 with these two. And that's going to, again, the inversion, it's going to be taken away. So that's going to give me that. Now write the remaining part. In this case, you can see that all the expressions now are reduced to the same amount. All expressions have two variables. So Theorem 7, it's not going to be useful anymore, because you have to have one variable, one more variable in one side of the expression. So, and now Theorem 7 is not good for me. So I have to find another theorem, and I'm going to go with Theorem 7. I'm sorry, with Theorem 6. So with Theorem 6, you can see that you have one variable inverted on one side and on the other side. This expression here with this expression here, and say I'm going to use Theorem 7. I'm sorry, Theorem 6. So that, because of Theorem 6, is going to give me Wy inverted, and then the inversion is going to be taken away. So W, and I write the remaining part, W zeta inverted. So now we're going to use Theorem 4, because if you see, Theorem 4 tells us that if we have the same variable repeated in both sides, then the extra term is going to be out. So here we have, we can apply actually this with both cases. So here we can see W plus W Y inverted, this one here is going to be disappearing, and W zeta inverted, this one here is going to be disappearing. So by using Theorem 4 in these three expressions, I'm going to have W or W or W. And of course we know that because of a postulate that this is equal to W. So the thing here is this expression, which is just a W, it's exactly the same as the original expression. It's this whole expression. So you can see the advantages of minimizing functions. It's obviously easier to implement something with just a variable w than implementing it with the expression, the original expression. Let's see another example, and this is just to clarify some theorem. So what if you have something like this? Well, in this case, I'm going to try to find relations again. You can try to find, and for example, I see that I have w here and I have w here, so I can say this one is going to be my a. Then you see that you have v here, or you have a different expression, it's b. So you can try to find any theorem, for example this one here. Okay, so you have now a or b. Then for this theorem to work, you would have to have v inverted over here. And of course you realize that this is not v inverted. So that means that you cannot use theorem 6. So if I cannot use theorem 6, I can try to find another one. But then again, I have to find for things that repeat. In this case, I already know that the correct one is theorem 9. So I have to find, in theorem 9, I have to find a variable that it's inverted on both sides. You can see that you have a here and you have a inverted here. So what it's inverted in one side and in the other one. I can start with zeta, so I can say a. What happens if zeta it's a? Then of course here I have a inverted. So I have one a and another inversion. Then in this theorem says that if you have this, then you have to have variables that are unrelated. So here you have some w, and w is not related in any way to these two variables. So this could be my b, and this could be my c. And then you realize that those two variables are actually combined. So because of this, you can see that with this theorem, it says that when you have these two combined, the combination disappears. These three terms, and by using theorem 9b, I'm going to reduce this expression, or I'm going to make this expression. Now, a common mistake here would be putting a 0 here. Be careful. This cannot be 0, because if it is 0, because it's ANDing, then the whole expression would be 0. Okay, this is going to be 1. And with that, this expression becomes... Now, you will not find any other theorem that can reduce this. Now let's see an exercise of finding the canonic form. And this is by using the Shannon's development theorem, which I already explained that it was in order to make an expression even or larger. So this one here is for getting the sum of products or the mean terms, and this one here it's to get the max terms or the product of sums. So you can actually use any of those formulas and get any of the canonical form. Even if you have here a sum of products, you can actually get the product of sums. And of course, if you have a sum of products, you can also get the sum of products canonical. I'm going to use theorem 10b to get the product of sums canonical form of this function. The function is going to be equal to, and then you have here to x1. So of course x1 in this case it's a. So it's the first variable. So you're going to put a here, and there you're going to OR this with the same function as above, but with a evaluating it as 0, and then b comma c, and then that it's going to be ANDed with the same variable, but in this case the variable it's a inverted, or the function of 1, or a equals to 1 comma b comma c. Now here's an important thing. This step, it's only to expand on variable a. So with that, you're making sure that all the terms in the function has the a variable included. Because if you remember, in order to have canonical forms, you have to have all the variables included. So we actually have to have 3 steps. We have to expand a, we have to expand b, and then we have to expand c. This is going to be equal to a, or then I'm going to put the function with a equals to 0. So if I put a here and a here and a here equal to 0, I'm going to realize that this is going to be 0, this is going to be 0. And of course, because it's 0 inverted, this is going to be equal to z. So actually, I'm going to have a z here. That's all I'm going to have, a or z. Then on the other side, I'm going to have the opposite. I'm going to have a inverted, or the function evaluated when a equals to 1. So when a equals to 1, then this is going to become v or c inverted. So I'm going to put that here, v or c inverted. So now you see that we have changed from a sum of products to a product of sums. And in both terms, in both sides of the equation, we have the letter a. But you can see also that in both sides you have the letter c. The letter c appears here and appears here. So all I have to do now is expand the variable b. And to expand the variable b, I have to do the same. I have to say function, it's going to be equal to the expression b, or the function evaluated with a, comma, and b being 0 and z, multiplied or ANDed with v inverted, or the function evaluated with a, b equal to 1, and z. I'm sorry, here it's b equal to 1 and z. All I have to do is evaluate this function with b equals to 0 and b equal to 1. And with b equals 0, if you have 0 here, that's going to give you, and with b equal to 1, this is going to give you, and then here an interesting thing happens. It's going to be a inverted, or 1, or c inverted. So that means that this whole expression is going to become 1. So I'm going to put those two expressions below. So it's going to be b, or the function evaluated with b equal to 0, which is that one at the top. So it's going to be a or z, then that multiplied by, so this, I'm going to distribute it to this and to this. So this is going to be equal to, and multiplied by v inverted, and there we have the canonical form. There we have a product of sums with all the variables included in it by using the Shannon's development theorem.